It's my pleasure to introduce Ivan Bazarov, today's speaker. Ivan began his studies in physics at the Moscow Institute of Physics and Technology, and then in 2000 earned his PhD from Far Eastern Federal University in Vladivostok, doing research in the area of laser plasma spectroscopy. In the same year, 2000, he came to Cornell, first as a postdoc working at CLASS, which is now CLASS, where he worked on the feasibility of an energy recovery linac as the next generation light source. As part of that, he led our effort on designing and commissioning a novel photo injector, which now is the brightest and highest current photo injector in the world, and is now becoming part of the new accelerator currently under construction at Wilson Lab, which is CBETA. And Georg told you about this machine a while ago. In 2007, Ivan joined the physics faculty at Cornell and has since then been doing research in photocathode physics, high brightness sources, beam dynamics, new optimization and control algorithms. In 2010, Ivan won a DOE Early Career Award to investigate the fundamental limits of beam brightness, again from photo emission sources. He's also a recipient of the 2015 IEEE Particle Accelerator Science and Technology Award. His most recent roles involve the Center for Bright Beams, which is our NSF-funded Science and Technology Center, where he now is a co-leader for the beam storage and transport theme after he has helped to bring the beam brightness production theme to life. So no surprise that talk today is about beam brightness, so let's welcome Ivan.
Right. So my task today is to tell you about the effect and that accelerators have on today's science, as well as to introduce you to the concepts of physics of phase space. And then I will tell you about the work that I was a part of in terms of pushing the frontiers of beam brightness. So let me start out by pointing out that the age of discovery, which was beginning from the 15th century, relied on powerful tools, the vessels of discovery. So you're looking at Magellan's flagship Trinidad, which, if you know your history, didn't make it in his circumnavigation. Neither did Magellan, for that matter. But nonetheless, we owe this brave men and these powerful vessels as media for discovery. Today's age of discovery has different ships of discovery. They are accelerators. They are among the most powerful tools of scientific discovery of today. And accelerator science is a collection of disciplines behind the art of science of building and operating these complex devices. So what you're looking here is a couple of accelerators at Cornell, housed inside Wilson Lab, Cornell Electron Storage Ring, as well as this CBETA accelerator that is under construction right now. What you may not know is that Robert Wilson, when he was the architect of that building, he designed it to look like a sailing ship. And also, unless you never been to the Wilson Lab, the first thing that greets you when you enter is the Wilson Lab ship figurehead. So this analogy runs very deep of accelerators being the modern vessels of discovery. So I will show a few slides to give you a big picture of the kind of impact that accelerator science has on today's society. Accelerators and beams as tools of discovery, they require three major parts. Beam dynamics is a discipline that studies behavior of beams, collective instabilities, and how to manipulate beams. One requires, of course, bright sources or sources of particles. And another building block is the accelerating structures, structures that require electric field in order to accelerate these beams. Then one moves into the kinds of research and types of accelerators that one has, beginning from particle colliders, light sources, sources of other particles, neutron sources that are used for structural matter studies, and various accelerators used in industry. This impacts many areas of modern science and society, beginning, of course, with the fundamental building blocks of nature, the study that high energy physics takes, on itself, synthesizing rare elements, studying advanced materials used in biological sciences, in medicine, as well as impacting industry and other sectors of modern society, security, energy sector, and the part that we excel as Cornell Accelerator Lab is training future workforce. Very briefly, accelerators by the numbers. Roughly $500 billion of end products are produced, sterilized, or examined using industrial accelerators annually worldwide. More than 24,000 accelerators have been built globally over the past 60 years to produce charged particle beams for use in industrial purposes. This number does not include medical accelerators that are commonly used to treat cancer. About 200 major accelerators are used for research worldwide with a consolidated annual cost of well over $1 billion. So with all that, you may wonder, what does typical accelerator look like? Well, there is no such thing, because accelerators, they scale from few millimeters to many to several tens of kilometers. Of course, the biggest and probably most famous accelerator today is a Large Hadron Collider situated on the border between France and Switzerland. That is the vehicle for discovery of Higgs boson. The LINAC coherent light source at SLAC in California is the first X-ray free electron laser, and its scale is about 1 mile. Then, God forbid you end up in the hospital and use one of these things, but these are medical accelerators. They occupy a large room in a hospital. In this case, we're looking at a 22 MeV energy machine used for cancer treatment. Bright electron sources, microscopes, are also accelerators, and they tend to have energies on the order of 100 kilovolts, and fantastic tools, and we have a very strong group here at Cornell doing that kind of research. Accelerators don't have to be large. First, Lorenz's cyclotron was small enough to fit on the palm of a hand. And this little device called a Nutristor is a source of neutrons, compact source of neutrons, which you can see is not much larger than a penny. Now, when it comes to common accelerator topologies, there are several of them. One starts with a source of particles. And oftentimes, that can be used directly, as is, with a short beam line. For applications that require higher energies, one relies on linear accelerators to increase energy by sometimes many, many orders of magnitude. If one takes this beam and sends it around, it becomes possible to, using the same LINAC, boost energy even higher. Or, as in the case of this very smart energy recovery LINAC, take that energy back out of the beam and increase beam power. And in storage rings, we deal with a very different approach. This beam is injected, accelerated to some energy, and then sent into the ring. And such a machine, beam properties are no longer defined by the source, but rather they are defined by the equilibrium of this beam circulating for billions of times in that accelerator. Next, I want just to give you a feel for the kinds of subsystems that are required in order to build a successful accelerator. As I mentioned, one starts with a source. So here's an example of Cornell high voltage DC gun, photon injection gun. Photon means that photons come in and electrons come out in this specific case. Vacuum system. In order to preserve these particles of high intensity, one requires excellent vacuum. So much so that free mean path of particles colliding is as long as the distance from the east coast to the west coast. Here you're looking at the SLAC X-FEL beam vacuum chamber. Next, we need magnets. How do we manipulate charged particles? Lorentz force. So here we have electric field, magnetic field. We put them to good use. These magnets are very demanding devices. They require excellent precision of fields, both in terms of spatial and component composition. Accelerating structures. Cornell is a leader in this area. You're looking at a superconducting RF cavity inside the liquid helium vessel, and electrons go, or other particles, through the structures to gain energy. Cooling system, be it a superconducting magnet or superconducting cavities, one tends to need something maybe not as big as this helium liquefier cold box of European spallation source, but nonetheless a cooling system to operate this device. Injection or extraction lines in order to take the beam to either experimental hole or to inject it into the main LINAC, one requires especially designed lines that consist of magnets and vacuum chambers. So you're looking at Cornell photoinjector merger section that takes the beam from our source and sends it into the accelerating LINAC. And finally, beam diagnostics. So here we rely on this to be our eyes and ears in terms of the properties that these beams have. And of course, all of the control is done remotely, much like you would control a spacecraft and or a nuclear plant for that matter. You're looking at NSLS-2 control room at Brookhaven. So only putting all these things together, such a complex device
like the relativistic heavy
ion collider at Brookhaven becomes possible. Next, I would like to tell you about particle beam frontier. So in accelerator science, what are the frontier questions that we are working on? So first, there is energy frontier, not in any particular order, I must say, but in energy frontier, the discipline is concerned with ways of generating higher and higher energies. Of course, this allows us to probe even deeper into matter, subatomic structure. Next, you can look at the intensity frontier. Intensity frontier is frontier of making rare particles abundant or making bright beams and producing lots of them. So high quality beams. And finally, this brightness frontier that I have highlighted, which relates to the fundamental property of beams, namely the density of particles in phase space. That's a single most important figure of merit that tells how useful these beams are for a lot of applications. It's to push this important frontier of beam brightness, Cornell is leading an NSF Science and Technology Center with a dozen of institutions across the country. And I'm going to tell you a few words about this. So, starting from our picture of how accelerator science relies on these three blocks, being beam dynamics, source technology, and accelerating structures, the Center for Bright Beams is modeled after those. In beam production, we create the particles to be accelerated, and in particular, high brightness or high quality beams. In beam acceleration, we design structures with extreme electric fields in order to accelerate them efficiently. And in beam transport and storage, we deal with issues of beam stability and preservation of brightness in accelerators. So this is how the Center for Bright Beams is modeled. Here you see about a dozen institutions spread across the country. As Matthias mentioned, I helped to establish a beam production team, and since then I stepped down, and two of my former graduate students, now assistant professors, are heading this team, and now I lead beam transport and storage team. So I'm going to tell you about some of the things that have happened recently as part of this center, as well as some of the things that preceded the center but made this center possible that I was a part of. Okay, so now I will start talking about phase space and its physics to introduce some of the key concepts. Phase space is one of the most powerful inventions of modern science. So that's a quote by one science historian, which I totally agree with. As accelerator physicists, it's our natural habitat to think in terms of six-dimensional phase space. So we have two transverse component, x and y, two transverse momentum component, px, py, and then energy and time. Then brightness becomes flux or current divided by six-dimensional phase space volume. And brightness is connected to such concepts as Lowell's theorem, beam temperature, coherence. Considering two-dimensional distribution of particles, we can think in terms of 2D microbrightness. And this microbrightness is basically probability density function of finding charged particles within a given phase space volume. Another important concept in the accelerator world is that of emittance, which is loosely speaking phase space volume or area. And it's defined as essentially in this picture as an area of this ellipse. And defined in terms of second moments. So what's so interesting about the phase space? It's a queer world, the phase space. So to begin with, the statement that Hamiltonian flow in phase space is symplectic. So what does it mean? It means that it's area, phase space volume preserving. For example, if you look at trajectory in phase space, well, first off, trajectories in phase space do not cross. But what's cool about any Hamiltonian system is that the volume remains conserved. So if you have initial distribution that looks like this phase, and then you have some Hamiltonian operator acting on it, you may end up with some weird distribution, but the amount of red here and here is the same. This is what we know as Lowell's theorem. So one would think with such a powerful, albeit somewhat queer symmetry, accelerator physicist's job would be easy. So we have this Lowell's theorem behind us, but turns out that things are more complex than they seem. First, chaos is more likely than not, even for a single particle. So those who studied analytical mechanics, we get to that part in the course where we study chaos. Those systems are perfectly Hamiltonian, and they are chaotic. Second, charged particles, they interact with each other, making the whole situation much more interesting. And besides, accelerators can be quite non-Hamiltonian. We'll come back to this towards the end of my talk. So now I would like just to give you a flavor of some of the problems that are bread and butter of accelerator physics. Let's start with the stability problem in rings. So what you're looking is a storage ring where electron goes around, or positron or proton or any charged particle, and you're looking at the phase space portrait as it goes around. Say I have placed my screen here and I record position, I record momentum, and with a properly scaled position and momentum, I get a rotation matrix in phase space. So that, by the way, explains why we call it phase space. So there's a phase associated with this rotation. And this linear optics will be made of the quadrupoles, dipoles that help to guide the beam, nothing else. And repeated n times, that gives this lattice. So lattice is the sequence of magnets that guides the beam. So everything is great, looks fairly simple. And unfortunately, or maybe fortunately, you cannot build accelerator using only linear optics. Turns out that whenever off momentum particles go through the system, they see a slightly different lattice. And if it's just made of linear elements, this lattice will be unstable. In order to solve this problem, we introduce special nonlinear magnets called sextupoles and higher order. And what they do, they are nonlinear, which is explained here. They map position, say, to position, but momentum has this extra x squared factor. And that means that the system is no longer linear. So now we introduce nonlinearity in our system, and things get interesting. Here you're looking at the phase portrait of such a ring with a single sextupole with some choice of this mu sub x, this tune as we would call it. And you see that there are some resonances going on. There's a region of stability, and then you see particles outside that are being lost. If you change this tune to, or this phase advance to something else, then you can get to a point where no orbit is stable, except the one at the very center. And minute offset will cause those particles to be lost. So it's our job as accelerator physicists to come up with solutions. In this case, it's just by changing the phase advance, this mu sub x, where you end up with a stable orbit of maximum area. This is known as dynamic aperture problem in storage rings. Well, let's talk a little bit about the tricky space charge. So electrons interact with each other, positrons, protons, and what you're looking at is a momentum transverse position, phase space evolution inside for the beam that experiences Coulomb repulsion in external focusing potential. So the particles can't go anywhere, but they interact. And you can note a few things right away, that emittance and brightness are not conserved. The area stays the same, but that doesn't really help me because I see a lot of structure here. You're looking at what would happen if you put screen at all of those positions. So you can see that it's a non-trivial picture that emerges. Furthermore, if stochastic space charge kicks in, after all, electron is to good approximation a point particle, then the volume that is conserved is no longer 6d, but it's 6 times n times d, where n is the number of particles inside a single bunch, say 1 billion. So that's not a particularly useful thing to have a 6 billion dimensional volume to be conserved. Very useless. One good thing about space charge, though, that from basic relativity, we can see that space charge forces scale as relativistic gamma 1 over raised to the power of 2. So which means that if you accelerate your beam quickly, especially if those particles are electrons, then you can freeze out the space charge. And because of time dilation, basically, electrons won't know that other electrons are there in the bunch. Well, so far I've been talking classical physics. So what about quantum mechanics? Does it matter? Quantum emittance is very simple to compute. It's h bar over 2 in proper units. So if we normalize it by mc, Ras mass c, then, for example, for electrons, we get emittances of 0.2 picometers. That's a very tiny value. So the best electron beams today have degeneracies which are on the order of %, or emittances that are tens of picometers. So we are still away from that quantum limit there. For massless particles, however, you would take this h bar over 2, you normalize it by the momentum, h bar k, and then you end up with a nice result that the emittance of light is wavelengths divided for 4 pi. And that's much easier to reach. And so in order to extend the concepts of brightness, emittance, and phase space to these quantum beams, all one needs to do is use the Wigner distribution. I will not go into the details, but it amounts to letting go of one property of phase space, that it can be locally negative. So we don't like microbrightness to be negative, but if we are to have quantum mechanical system, then we must allow that for things like interference. So what you're looking here, this work we did with Andrew Gasbarov, my undergraduate at YZ, who, by the way, first authored this paper. So undergrads can really do that. Phase space of X-rays from an accelerator, and you're looking at these blue areas. Those are the regions where this microbrightness is negative. The information contained in a plot like that allows you full characterization of your beam, including things like what mode composition you can do. So in this case, you can see that there are two modes that this pattern is made out of with fractions of 0.8 or 0.2. All right, so now that I told you some basics about physics of phase space and brightness, I would like to tell you about how we attack this brightness frontier. There are three things that we do, a three-pronged approach. We conserve phase space, we control it, and we cool it. So for conservation or preservation of phase space, it amounts to producing the brightest beams you can, and then making sure that this emittance, this phase space volume, does not grow as the beam is being transported from the source to the point of application. For control, we talk about advanced algorithm to tune our accelerator, which tends to have hundreds of degrees of freedom if it's a large machine. If it's a smaller machine, it could be a couple of dozens. New diagnostics and nonlinearities control and collective effects. For cooling of beams, yes, you can cool beams. We are looking at cases beyond Hamiltonian systems, so beyond Liouville's theorem. We introduce some kind of damping, some kind of energy loss mechanism, and we can reduce phase space, which is the right thing to do. You don't want to increase phase space, you want to reduce it, because brightness is inversely proportional to that. So I will start by talking about this conservation of phase space, and let me introduce to you the brightest way we know at the moment how to make electron beams. It's called photoinjector. This is a very schematic view. Later I'll show you how the real device looks like. So we take a material, photocathode, we place it in high gradient environment, say something ideally 100 megavolts per meter, which is allowed by accelerator standards. We shine the laser pulse, and out come electron bunch. In order to push brightness, we have to understand what is the fundamental limit or how bright a beam can be made. Turns out it's a nice, simple problem that if you put your mind to it, you can solve. So recall that brightness, say in 4 dimensions, just the transverse dimensions, will be proportional to the number of particles divided by the emittance squared, the phase space volume for x and y. The emittance is proportional to how big the laser spot you can make, and proportional also to the momentum spread, which you can write in terms of this mean transverse energy. We like this definition, which is just that, transverse kinetic energy of photoelectrons. You can see that if you divide things out, it's just the momentum spread, transverse momentum spread. If you figure out the number of electrons in a bunch per unit area, then you can combine this relationship to get the brightness. Where does this come from, this limit? Well, it comes from the so-called Child-Langmuir's law, and it's and depends on specifics of geometry of your bunch, but its simplest incarnation, it's basically Gauss law. So recall that in order to extract some kind of charge density, you have to equate your charge density to the electric field that you apply, right? So in the course that I'm teaching, undergrad course right now, that's one of the equations that's given to you during exam. So that's all you need. So when we formulated this limit for the first time, it really allowed to put this research on a more firm ground. So this formulation that we did ends up being very simple. In order to increase brightness, you have to increase electric field that is available to you, and you have to decrease mean transverse energy of photoelectrons that are being emitted, ideally making it 0 or as small as you can. If your pulse is not short, but rather longish, then a dependency is modified, and you can get even higher brightness at the expense of longer pulses. So let me show you what it boils down to by one example which was at the title slide of my talk, ultra-fast electron diffraction imaging. So in this type of imaging, like with any diffraction, you send a wave, ideally planar wave. In this case, the wave is electrons. Recall that electrons are a wave, not just a particle. And looking at this crystal that we have with the lattice unit lattice of A, you will get diffraction pattern. Unfortunately, electrons do not come perfectly collinear. Instead, you will have some kind of spread of angles in the beam, and which will smear the diffraction pattern. And of course, if you keep increasing this angle, then at some point you will lose all of the diffraction data. So the thing that we care for is the coherence length. That's the lateral dimension over which phase of electron remains well defined. And that, as you see here, is inversely proportional to the spread of this angle, so momentum, in the transverse direction. This is reduced Compton length. So the work that my former grad student and at the time a postdoc Colin Gulliford and scientist Adam Bartnick working in our group, what we did, we came up with a scaling that shows what are the key points of impact that one has to push in order to increase the coherence length more and more. You need it to be large enough so that you can resolve some structure with large unit cell. So if it's a protein, its unit cell, I don't know, 3 nanometers. If it's a metal, it's few angstroms. You'll see why it becomes relevant a little bit later. So one basically has 3 things that one can push in order to make beams brighter for this application. There's the cathode field. So the higher the better. There's mean transverse energy, this kinetic energy in transverse dimension, and the smaller the better. And then the final spot size, if you can make it very large, you get less spread in angles and therefore more coherence. But that's a costly direction because you want to set the sigma x to your sample size, and those samples tend to be tiny. So you can really push it. Instead, you have this factor which we call cathode emittance preservation ratio. If it's 1, it means that all the emittance from the cathode is preserved to the point of my experiment. If it's 0, it means I preserved none of it. So it's somewhere in between. So this leads us to this points of impact, like I described. In particular, for this emittance preservation, one has to deal with this nasty space charge and perform a trick that we call emittance compensation. And that requires very careful tuning and beamline optimization to make that happen. For cathode field, well, it would be nice to have arbitrary large electric field, but that doesn't work. Instead, you have breakdown phenomena that limit your field. So with the field available, you begin optimizing your gun geometry to take full advantage of the field you can have and still have a working device. And with the mean transverse energy, which you want to push down, we want cold beams. We want it to be 0. And that's a fascinating area of research that I'll talk about and the things that can be done there. So let me start out going through these points of impact, and we'll begin with emittance preservation. So here, we were the first ones to use multi-objective optimization in accelerators. What does it mean? Instead of optimizing just for one thing, in accelerators, we tend to have multiple parameters. And not all of those things are input parameters. Some of them are output parameters. So here you see, for example, the emittance being the vertical scale and bunch length being the horizontal scale. We want to go to 0 emittance, which means infinitely bright beam, and want to go to 0 bunch length, which means highest temporal resolution possible. So this system, unfortunately, is very nonlinear. You have the space charge forces. Remember that weird phase and how deformed and how hard it is to predict what will happen. Instead, you throw this multi-objective genetic algorithms on this problem, combined with the state-of-the-art beam codes. And one can map out so-called Pareto frontiers, Pareto optimality. which is kind of like the nature works when it comes to processes of evolution and natural selection. Nature does not optimize one parameter. You have a competing optimization, and you're mapping out all possibilities along that trade-off. And this is what this Pareto runs are. What we have done over the course of several years, we have perfected this technique so that we are at the point where for photoinjectors, we get excellent agreement with measurements. Our main measurements were done at this photoinjector. Many students, so you can see some of the plots here that I'm showing. This is how the phase space, measured phase space looks like. And computed phase space looks very much the same. And we have predictions of the beam current, and which we compress. And you see that there's a beautiful agreement. Many students worked with me on this project, including a graduate student, former graduate student Colin Galliford, now Dr. Galliford, and undergrads Igor Sinderovich, Manu Lakshmanan, and Alan Kim. Now, this approach is just great. If you haven't heard of multi-objective genetic algorithms, think about using them. You may like that. So they're now used for all photoinjector designs and to optimize storage rings. How about this single shot femtosecond electron diffraction? So these machines are compact. By the way, just to give you a scale, this accelerator is, you can see here, scale 20 meters long. So it's still a big and expensive device. Whereas for electron diffraction, you only need 100 kilovolts, or perhaps even less or more, depending on what you're trying to do. And we have such a setup in the basement of Newman. William Lee is graduate student, supervised by Professor Maxon, who is the lead man on this. And this setup is capable of single shot electron diffraction. We want to do it single shot. So as each pulse gives us this enough data to reconstruct the positions of atoms. For this, we need on the order of million electrons per pulse. Well, it turns out that that's a little too many, because when they are compressed for the size and the duration that we want, space charge tends to be too strong and ruin the show. So here I have an example of a protein, a rhodopsin, light sensitive, and using coherence length, the state of the art. And you can see that with a 2 nanometer coherence length, which is very good by today's standard, all the diffraction data is lost. So what we do, we throw our machinery of this multi-objective genetic algorithms, and we tune the beamline, and we play with all the magnet settings and the RF compressor. We come up with the solutions that result in coherence length, which is good enough to resolve the structure. So here's a plot from the paper we did, which shows that for coherence length of 20 nanometers, we should be able to get this good coherence length with the femtosecond resolution of this ultra-fast diffraction. And when you do that, you recover the diffraction pattern. This is computed, by the way, so we have not taken data yet. We're working on it. And in this particular system, what's interesting is to understand the role that light plays in rhodopsin. You have lumina rhodopsin, which is the light-excited version of this protein. And what you're looking at, that with this coherence length, it would be enough to resolve the diffraction pattern difference between how atoms moved. So that's great. However, one thing that we noticed that emittance that we are starting with, which by the way requires, as I'll tell you later, advanced cathodes that my lab knows how to make, the final emittance grows by some factor. The factor can be from 2 to 10. That's a lot. So when it's 10, you can say, well, did my cathode emittance even matter? So this particular application is very challenging. And we see that there is this residual emittance growth that comes from somewhere. So where does it come from? And there can be many sources of emittance growth. It can be element aberrations, slight emittance mismatch, nonlinear space charge, just to name a few. So my PhD student who works with me, Chris Pierce, came up with this emittance component analysis where we are able to pin down our enemy so that we can understand how to fight it. So it's actually nonlinear space charge that is limiting us in this case. And so, can we do better? Turns out that we can, but we have to become smarter about things. So beam core, consider beam core in phase space. That's a little different than beam core just in physical beam. And turns out that for small current applications, it's easy enough to collimate parts of the beam. And you can imagine that this phase space here, which is some measured phase space that we have, and as I start clipping halo, the emittance gets better and better. Of course, the fraction of the beam contained gets smaller and smaller. And so in the center of this phase space, I will get the value that I can call core emittance, which is related to this maximum phase space density. And that turns out to be a strong invariant. What I mean by that is that space charge doesn't seem to ruin it nearly as much as it does the full emittance. For example, here's results of simulations. You are looking at a case where emittance grows by factors of 10. What I'm showing here is the core emittance change. And you can see that the core emittance changed only by 20%. So the core of the beam still carries the information about the photocathode. And improving this, improving photocathode will improve performance of such a device. Now, you could think that we could set mean transverse energy to smaller and smaller values until we hit this nice number 0, where things get really exciting. Turns out that as you do reduce mean transverse energy, you run into disorder-induced heating effect. Jared Maxson, at the time when he was a grad student in my group, together we formulated, and colleagues from Berkeley lab, this disorder-induced heating, which is very simple to understand. You start out with randomly created electrons in your bunch. And because of this random placement of particles, they relax very quickly to some more average distance. And as they do, which happens very fast, and you can think of it as a special case of plasma oscillation, single species plasma, it happens on a picosecond scale, it heats up this core emittance. So, and as you make beams denser and denser, this limit gets worse and worse. So this is likely to be the next practical limit that we will be dealing with in the arena of high brightness beams. I'll continue guiding you through these points of impact. Here we have cathode field and mean transverse energy. They are sort of related. So how do these photoemission guns actually look like? This is on the order of a meter. This is on the order of slightly less than a meter. This is on the order of a meter. So we have choices of how to generate these extreme high fields. We have DC guns. We have normal conducting RF guns. We have superconducting guns. Each has its pros and cons. For example, in DC guns, we have limited gradient and energy because of the breakdown being worst in the DC environment. But we can move cathodes in and out. We can generate excellent vacuum. In the normal conducting guns, we have the highest gradient possible because these are AC fields and they're pulsed. And we can get to 100 megavolts per meter, very nice field. But the vacuum is poor. Just to support those fields, currents have to flow through the copper structure. Usually it's made out of copper. And when they do, they dissipate lots of power. And those of you who do ultra-high vacuum work, you know you don't want something hot in your system. But the walls of the structure become hot. Superconducting RF guns, they're really cool, literally cool, very cool. So, and they can give you continuous operation with higher field than DC guns can. They have excellent vacuum, but the problem that people are plagued with in this device is cavity contamination. You have to move cathode in and out, and those people who do superconducting RF research, they know, don't move anything in and out when you're building SRF cavity. So our lab has a history of innovation in these sources. I told you that we have limited gradient. We have to take full advantage of it. So what do? We adjust, for example, cathode-anode gap. That may sound like a somewhat weird thing to do, but in the physics of breakdown, it's very complex, and it's not the field that limits the background, the breakdown. It has a dependence on the gap. We optimize geometry of the cathode for best emittance. Because we want to use best cathodes, we make other modifications, such as biasing the anode in order to block ions that can be created downstream, go back to the cathode and kill your cathode. So again, when Jared Maxon was a grad student in my group, he built this gun. I will tell you that building a gun like this banishes all fear out of you and makes you ready to face any challenges in life. So I think Jared will agree with me. And so what this machine now drives the C-beta accelerator, and also a copy of it is at Brookhaven running low energy rig cooler. My other student, Harry Lee, she built another gun, which is this 200 kilovolt DC cryo gun. So the key feature here, there are a couple actually. So one is that we're able to cool cathodes down to a few tens of Kelvin. As you'll see shortly, what that accomplishes, it cools electrons as well, which is very, very interesting. And it also demonstrated very good field by DC gun standards. Alicia Galdi, who is the postdoc working in our group, she is behind this new source, which will cool cathodes to even low temperatures, have very respectable voltage and very high gradient. And we expect that this system will be used to measure mean transverse energies to record resolutions, like milli-electron volts. You're seeing here also a picture of one of our undergrads in the group, who now moved on to his grad school, Sean McBride, and he was behind figuring out the mechanism for transferring cathodes from one system to another, which is not trivial. So that brings me to the photocathode physics and design of photocathodes. The photocathodes used today, they have this mean transverse energy on the order of electron volt, maybe down to 100 milli-electron volts. And we want to go in this direction, want to go down, because as we do, brightness actually goes up. Yeah, forgive me for brightness going down. So the cathodes used today are somewhere here or whereabouts. And the way we build those cathodes, we follow some witchcraft and recipes, pretty much. What my group has been doing is pushing this with optimized electron transport, so some cool condensed matter, minimizing surface roughness, and cryocooling cathodes. But in order to move to the ultimate values where disorder-induced heating will start to dominate, we really need single crystal ordered materials with no surface disorder scattering, where electronic band structure will be determining our emission properties entirely. So let me show you some of the examples of what we were doing. So cooling photocathodes. What happens if we cool disordered cathode to cryogenic temperatures? We did that, and what we discovered that if going to the threshold of emission, think of a Fermi-Dirac tail and free electron model, and this shrinking Fermi-Dirac tail is you cool the material and you're picking only electrons from that tail. So sure enough, it's, you can actually cool electron beams just by cooling the substrate. So we did the measurement from reducing temperature from the room temperature to liquid nitrogen temperature, and we saw that the mean transverse energy was reduced by roughly factors of 2. So 2 PhD students were instrumental in this, Harry Lee and Siddharth Karkare. I must add that I'm only showing pictures of grad students, former grad students, and postdocs. So there are, of course, important other people who are behind these results. More recently, Siddharth Karkare, who is now an assistant professor at Arizona State University, he has demonstrated that this mean transverse energy could be reduced to single-digit milli-electron volts. He used the material copper, so it's a crystalline copper, and in order to measure these small mean transverse energies, they had to develop their own diagnostics with delay line detector, sort of a different version of ARPAS that some of you are familiar with. And it's a very exciting result, except for one thing. This quantum efficiency number, which ideally we want to be 1, is 8 decades below. So that might be an issue. And in fact, this road of trading off
emittance for efficiency
at some point stops working. Why? Because in order to extract the same number of electrons, we have to pump more and more laser energy. As we do that, we have to be prepared for things like 2-photon processes, which will give extra energy and extra emittance. And static photoemission models no longer apply because we have to account for phenomena that are shown here, where you can grab some of the parts of your distribution, this Fermi-Dirac distribution, and promote them to higher and higher energy so that your transverse energy will also grow. So work that Jay Kwan-Bei is the first author of that we have recently submitted shows how to account for this effect in metals. And we think we understand it. We need more measurements, and more importantly, we need to come up with models for semiconductors where the situation is more interesting because we want to use semiconductors with high quantum efficiency, not metals. Well, can we cool electrons without cooling? Yes, we can. So those of us who are in condensed matter business, we know that all you need is a small effective mass material, because small effective mass acts as index of refraction. So by making small effective mass, you can essentially take advantage of narrow cone that will be emitted because of Snell's law equivalent. So here, mean transverse energy would be the transverse, this horizontal extent of this picture here. So we can start with computational screening of many, many materials. We can go and look whether we want to use metal or semiconductor. We can screen for low effective mass, check that optical excitation is what we want, and get some prediction of low mean transverse energy and high quantum efficiency at the same time. Well, as it turns out, the promise is there, but progress has been slow. A couple of reasons. Complete mean transverse energy models are costly and difficult. We need close integration with experiment. And then physics of real life can screw up even the best simulations. So one does not simply grab bull by its horns. So the part of the center is to tame the bull in a methodical fashion. So here you see the idea that we want to use and pursue. We start with a screening of materials. We find good candidates and do the best growth we are capable of with the best surface we can generate. Then we perform beam tests and measurements, and then we feed back this in a loop. So we do iterations. So you can see that this team of people is taming this bull. Let's come back to the three-pronged approach, the problem of control. This is an important problem because many accelerators, most of them, they have many degrees of freedom. And in order to tune them, we have to come up with a smart strategy. It's not physical to tune 100, not physically possible to tune hundreds degrees of freedom and get result in a reasonable period of time. So what we are doing here, we're using Caesar, which is a unique test bed for online optimizations. And we can test various strategies for optimization. Online optimization, meaning you sit in the control room, you press a button, and something good happens. What you are seeing here, we have used this approach, sloppy models and genetic algorithms, to make this faster correction. Sloppy model refers to the fact that not all 100 degrees of freedom are equally important. In fact, you can form linear combinations of those magnets that will have exponential importance. And then just using a handful of them, you can get most of the improvement that you need. Now we're working on, so here you can see the effects that we can have for this new optimization procedures. This is the direction of improvement, and this is direction of improvement. And now we're working on generalized platform to extend our results to other accelerators. Will Bergen, Cameron Duncan, grad students who are doing this work, and Danilo Liarte, Matt Endorf, and Vardan Hachatyan are the postdocs who are helping there. Another frontier that Caesar is attacking has to do with this cool. So I'm coming to the last C, here the idea is the following. Storage rings that have positrons or electrons emit a lot of radiation. So when you emit a lot of radiation, it means things get cooler, or potentially can. They can also heat up. But in hadron beams, very little power is radiated because relativistic gamma is much smaller. Since the mass is much, much higher, so beams tend to bloat and be limited by the source. Van der Meer came up with this idea of stochastic cooling, for which he got the Nobel Prize in 1984. And in his idea, it's a very cool thing to look at, the kind of publication he put out. It's actually like a note. It was not even published. So he just wrote a note, and voila, he got Nobel Prize. So that's the way to do it. So the idea that he put forward is that there is intrinsic noise in the bunch. If you can detect it, then amplify it and feed back on it, then you can correct for it. And you do it on each turn. And overall effect is that you're cooling, you're adding damping term, and your phase space shrinks. What we are doing is this optical analog of stochastic cooling, where pickup and kicker are actual undulators, and they generate long wavelengths light, which can be then amplified and act back on the beam. The guy who came up with this was Alexander Mikhailichenko, a very smart accelerator physicist who passed away this summer. So what you're looking here is a optical stochastic cooling bypass that we will be installing at Caesar to test this method for the first time anywhere. Let me move on to other applications for cooling. So here we have electron cooling of hadrons. So what changed? Now we are talking about using electrons, overlapping them with ions in order to increase the temperature of electrons but reduce the temperature of ions. Because ion beams, as I said, tend to give too large to give good luminosity. And this, by the way, here, you're looking at the next frontier machine that the Department of Energy is planning to build. It's called electron-ion collider. Think of it as a huge microscope for to look into gluon physics. The problem with this approach, well, first of all, the required electron beams do not yet exist. One requires currents on the order of 100 milliamps, and they have to come not from a storage ring, but from a LINAC and a good source. And such beams can only be made from energy recovery LINACs with high current sources. And that's precisely what Cornell is doing. You heard that talk from Georg Hofstadter about this accelerator that we are putting together in Wilson Lab. There are several interesting things. I won't go into detail. But one thing that I would like to emphasize that we are pushing the beam power frontier. In order to cool these ions, one needs lots of power. And these lines here in that direction, they push power. So 10 megawatt beams of high quality electrons, that does not exist. And people are talking about building this electron-ion collider quite soon. So this problem has to be solved. And then brings us to this topic of cathode lifetime. So why people propose these things if I said these beams do not exist? Well, our group powered through this result where we improved cathode lifetime by significant margin that now these proposals will be received and not laughed at. So this Cornell injector that I've shown you already is where we did this work. You have to understand that when electrons are being produced from a photocathode, it's a very toxic environment for cathodes. Electrons come out, they hit residual gas. No matter how good your vacuum is, you'll always have some of those. You produce positive ions, they go back, they smash into cathode and ruin it. So it's a matter of time when that will happen, but that will happen. And for example, a single high voltage breakdown in a gun is enough to ruin your cathode. So if you want to operate $1 billion facility, you want to think about how to address that. And so what we have done in our group, we through a series of research, improving materials, improving our machine, we were able to push beam current from the highest value of about 20 milliamps to 75 milliamps, and also to increase the charge lifetime by more than factors of 10. So let me also mention another exciting result. There's another interesting application which involves spin polarized photocathodes. You can make electrons that will have spin orientation, and for this electron-ion collider, which is the huge microscope, you want spin polarized electrons to be able to look into the physics of nuclei. And how those electrons are made. They are made using superlattice gallium arsenide. You can see here spin orbital coupling, and superlattice gives you strain, and then with the circular polarized light you can come in and excite polarized electrons, which is what you want. The problem with these cathodes, this gallium arsenide, that they activate it with a single monolayer of cesium, which is super sensitive. You can see here an example of us trying to run with this cathode, and the lifetime is on the order of minutes. You can't really do much better. So when people looked at these options, who were designing this electron-ion collider, they said they had this option that was both cheaper and higher performing, and they had to retire it because they said, well, that's a practical challenge that nobody solved. So if the lifetime of these cathodes can be improved, then not only EIC becomes possible, but one can also use spin polarized beams in more laboratory settings. So we have undertaken this work where we applied protective coating, and to skip to my conclusion, since I have run out of time successfully. So I will just show that we were able to show that this coating that we applied does not ruin spin polarization, because that's one parameter you don't want to screw up. And it also gives lifetime, which is factors of 5 better. So this was a result that we did and published, and we keep trying. So just a couple of weeks ago, we came up with a new alternative material that improves the lifetime of essentially 2 orders of magnitude. What that means is that now you can make these spin polarized cathodes at some factory and ship them to your facility, for example, and also use it in other diagnostics that involves spin polarized beams. So the grad student behind this work is Jake Van Bay, and undergrad RU student Phil DiGiacomo. So this is my last slide, almost. I want to say that I have tried to portray to you that accelerator field is now this interdisciplinary team effort, and that we know and moving aggressively to improving brightness by 2 orders of magnitude. We see and that applications and uses of accelerators will diversify, and compact, new powerful machines will be more widespread. And Cornell is to remain at the frontier of this exciting field and technology and education in the coming decade. So beams like vacuum, accelerator physicists do not work in vacuum. So I would like to acknowledge many of very bright people, PhD students who worked with me and continue working, many undergrads that are very talented and who made many of the things I showed possible. For the injector bright beams group at Cornell, especially Dr. Luca Coltrera and Professor Jared Maxson, ERL-C-beta collaboration, especially Professor Hofstetter, Caesar and optical stochastic cooling team, especially Professor Rubin, CBB, and especially our Richie Patterson, whose energy and enthusiasm very much enabled that center. So with this, I will stop and take your questions. Thank you.